Alright, hell yeah. So this video is all about angular momentum, and this is going to be pretty cool because we're going to be able to analyze this problem. This was a problem in a textbook that I came across. Very common. You have a square rigid body, and then it's traveling with a velocity, just sliding along the floor, and then it hits an abrupt edge, you know what I mean? So all of a sudden this thing starts to tip over, you know what I mean? So this instantly becomes a hinge, and they say this is an inelastic collision. So that means that an elastic collision would be like, whoa, this thing comes in, hits this bumper, and then just instantly starts going the other way. So it would come in and hit the bumper and then go that way. A totally inelastic collision means that it comes in and hits and then basically kind of meshes with that point. There is no rebound effect, and essentially what you can imagine is at the instant it hits, it creates a hinge. So, you know what I mean? So maybe you just like weld a door hinge at the moment that it hits, and then it has all that velocity. So it's basically rotating about this point. Now, to solve the problem, you would say that the angular momentum about this point, or this axis, this square, it is a three-dimensional, you know what I mean? So if it's on a flat surface, you know what I mean? Here's the abrupt edge that it hits, and then it starts to rotate forward. Okay, so, but they say angular momentum is conserved about this point. And then, you know, if this is your first time with these, and I had no idea what was going on the first time. It just made no sense to me. So we're going to talk about this by using a catcher. And we're going to talk about a scenario that's going to make this make sense. Now, in the end, I think it's really easy to talk about linear momentum. So let's say we have some sort of mass, it has a velocity, and booyah, we have momentum. Momentum is usually this kind of lowercase p, and momentum, the equation for it is just mass times velocity. So anywhere that we have a mass, this mass has a velocity. Cool, we have you know, some sort of quantity of momentum. We can actually kind of put these, you know, chunks of mass together, and hey, maybe we actually do have a square. It's like kind of 4 chunks of mass. Each of them has a each of these has a mass, and each has a velocity going in this direction. So then when we go back to our square down here, yeah, we can kind of break this up. We can say, hey, that's a mass. You know what I mean? Maybe that's a chunk of mass, and this is a chunk of mass. So when we come in, we can see that when this hits, yeah, this chunk of mass was traveling with this initial velocity. We're just going to call it v naught. But now this chunk of mass has a velocity of 0. So at impact, this chunk has a velocity of 0. Now, something happens because we go from like linear velocity to pure rotation, and then so we have an omega, a radians per second. You know what I mean? That's just going to be your radial speed in radians per second. Alright, hell yeah. And so when that happens, well, sure, this chunk of mass had that initial v naught, but now it has, the second it impacts, well, because you have a tipping, and then you have a angular speed, you know what I mean, this will have a tangential velocity, you know, because now it's like kind of rotating around this axis, and so it's going to have, this thing's going to instantly have a velocity. We're just going to call it v, and then the velocity of that, this side is s, this is kind of our radius, but it's going to be so the velocity is going to be omega times the radius. That's kind of the equation for velocity, and so it's just going to be that omega times s. You know, it's omega times this distance. So this will have, now the question is like, well, is this initial v naught going to be equal to that velocity? You know what I mean? And I guess the bigger question is like, cool, this chunk of mass came to a stop, and maybe this chunk of mass actually goes faster than the initial velocity, so its v is greater than v naught. But now the question, I guess that was just a rambling to ask, you know, if this thing is sliding in, and we divvy up all these chunks of mass, and they all have a, so all of these chunks of mass, of m, have an initial velocity that way. And then once it hits and starts to tip up with this omega, about this point O, well, hey, that chunk of mass has a velocity of 0, but maybe this chunk of mass has a velocity of like 1.5 v naught. You know what I mean? So now the question is like, hey, is every chunk of mass, is linear momentum conserved? That was the first question. I'm sorry, I just can't even spit it out. But yes, was linear momentum conserved over this whole square? And the basic answer is absolutely not. When this impacts. All right, and I don't think this is a dumb question, because angular momentum is conserved about this point. I'm just like, well, is there no force on this point? Like is it coming in and it hits and it just doesn't feel anything? And no, absolutely not. There is a force that is pushing this direction, that is resulting from that collision. Whether it's elastic or inelastic, it don't matter. You're going to have a hell of a force on this this square. Now, in just general terms, if this is your mass and this is your square, and then you come in and then you have some sort of velocity, and then all of a sudden at this point right here, you're going to generate a force and maybe bring it to a stop. Sure, that's going to bring this whole chunk maybe to a stop. But our force is just on this lower leading edge. So it doesn't bring the cube to a stop, but it does make, as long as it's completely inelastic, it kind of makes this as a hinge, and then the rest of the cube just tips about this hinge. You know what I mean? So it'll come in and then just kind of tip, and then kind of rotate, kind of topple over itself. But this force does act on the mass, and you will have a change. I guess you could put it this way. You'll have a change in the total kinetic energy. So linear momentum will be reduced, so that number will go down. So if you actually, cube up this entire thing, and then you solve for linear momentum, it's going to be, if this is like m1, and then we have a tangential velocity, we're going to say a velocity tangential 1. Coming in here, this was going to be our m1, and it had a velocity v1. Cool. So m1 v1, and then this had a velocity m1 v tangential. Cool. So the initial angular momentum, and then we'll just say final angular momentum, this number is going to be bigger, this number is going to be smaller. So hell yeah, the initial is definitely greater than the final. So you can add up all these masses and these velocities, but we're going to explore that. Alright, hell yeah. And so now this is where we're going to transition to our baseball players, because we have to understand what momentum is. We need to know what linear momentum is, and then what angular momentum is. Angular momentum gets this letter L. It is a vector, and it's going to be, what the hell is it? It's oh yeah. So if you forget what the equation for angular momentum is, do the equation for a moment, or a torque. What is it? Yeah, a moment. So if we do m, a moment is a force times distance. So it's f dot r, you know what I mean, or a force dotted with d, and it's not even that. It's a cross product. My bad. Holy hell. Oh, yeah. And you probably will do it like R cross F. There you go. So it's R cross F or D cross F. But basically R cross F. So that's what a moment is. And so I would always, any angular momentum problems, hell yeah, draw a door. And then draw kind of your hinges. And then we're going to put a force on the doorknob right here. And from the hinges, here is the distance away from the hinges. And this is going to be our R. And so here's our vector for our distance. From the hinge, this is the point we want to analyze. We want to see if there's any torque, moment, or couple. I guess you wouldn't call it a couple. But you would call it a moment or a torque on these these hinges. And maybe you wouldn't even call it a torque, because I don't know, maybe the hinges just are frictionless and you would just call it a moment. But anyway, you would use the right hand rule. You take your right hand, you put it in the direction of your distance to the force. So there you go. And then you sweep your fingers in the direction of the force. And wherever your thumb points, that's going to be straight down. That is going to be, and I just do double arrows on this. And so what this is going to be your moment. So there you go. And it's a vector. So the moment vector is in this direction. It is applied on these hinges. This moment through the path of the hinges is what allows the door to open. This is the number and the direction and location that causes the door to open. You know what I mean? If you were able to, well, if you put the doorknob here, this moment would be half. You know what I mean? If it's half as close to the hinges, same force applies half the torque or half the moment. All right, so hell yeah. And the other word you can use is leverage. Like obviously, if the force is here and you have a doorknob out, heck yeah, you're putting a leverage. You know, you're applying a force, but it's the leverage is this distance away. You know what I mean? That's the most important thing. Because if you go to open a door and, you know what I mean, sometimes, like, yeah, I've done this before. Sometimes you have, like, panels in the door, and you'll have, like, it'll be recessed, and you can get your fingernails and start to just pull on those. And they're not in line with the hinges perfectly. They're just a little bit offset, so you can actually open the door, you know, in very odd ways. But I guess the take-home point on the door, if you put the force, because this will go back to our catcher. This is kind of the scenario that we want to analyze, is when a ball hits the catcher right at the center of mass, there is no angular momentum. And then so if the ball is way up here, you know what I mean, and this is the catcher's center of mass, to stop this ball, this catcher has to apply a force right here, and it's a distance away, you know what I mean? So we have this like R cross F. So you're going to have like a moment. A moment is necessary, or a torque, you know what I mean? Because that's what, and we'll talk about that a little bit more for angular momentum, is that if you want to change the angular momentum, you have to apply an external torque, you know what I mean? So this is what they're talking about. This catcher is applying an external torque. This catcher is putting the hand up at a distance and then applying a force, and that's going to apply an external torque. So the angular momentum from, let's say, this point, we're going to call this point O, the center of mass, and we're going to get to that again, because with angular momentum, you have to choose the point you're taking in your angular momentum about. You know what I mean? All right, hell yeah. So let's get back to the equation of angular momentum. We saw that that a moment is leverage of force times distance. It's force and distance, and it's that leverage. So angular momentum is well, I don't even know why I struggle with this. It's R cross the linear momentum. It's a distance away from the linear momentum. You know what I mean? And so we'll write it one more time, because it's R cross. M is not a vector because mass never changes. You know what I mean? But your velocity can. So oh yeah, let's go back to this, because these have to be at right angles. So if you're like, what the hell is the cross product all about? Cross product means that when you multiply these, they only have, you know, juice if this is 90 degrees. You know what I mean? So anytime you see a cross product, you know what I mean, you have a force going this way, a distance going this way at a 90 degree. If you have that 90 degree angle, hell yeah, just multiply the two numbers together. You know what I mean? And if you don't, if you have like a 0 degree angle, or let's say this is a 180. So we're going to try to open the door by putting a force this direction. Now we have 180 degrees. And this is you're not gonna be able to open the door at all. You're putting no moment on these hinges. You're just putting a force through the hinges, and that's the scenario where that we'll talk about when someone throws a ball to a catcher and it hits them square right in the center of mass, of their glove and their body. The system had no angular momentum. There was linear momentum, but the angular momentum of the ball and at the point O, of the center of mass of the catcher, that angular momentum is 0. Compared to this, if the ball is thrown higher, well, hell yeah! From here, look at this. You have a distance r, and then this baseball has a mass, and guess what? It has a velocity going in that direction. And look at this. This is a 90-degree angle. So hell yeah! Just like a force can open a door, because the doorknob's a distance away from the hinges. And that's called a moment. This has angular momentum because momentum is going to be that distance times that linear momentum, or that mass and velocity. So here's our distance away, and guess what? This baseball has a mass and it's got a velocity that's perpendicular, 90-degree angle. So hell yeah. So the number for this, the angular momentum for this, the number is this distance. Maybe it's like, 1 meter, and then this the mass of a baseball. I think it's, I don't know, like 100 grams, like 0.1 kilograms. So a tenth of 2 pounds. You know what I mean? And then I think it's 0.1 kilograms, and then the velocity coming in. Holy Toledo! I guess it could be going 100 miles per hour, and I think you would just half that. You know what I mean? So let's say it's going like 45 miles per hour. I'm sorry, 45 meters per second. So now we can actually get a number for this. If we want to put a number on it just right away, we have a distance of 1 meter, a mass of 0.1, and a velocity of 4.5. So we got a number of, so 0.1 times 45, is going to be 4.5. Booyah. Who cares what the units are? At least we have some sort of number on the angular momentum. Now here, you had no distance away, so you'd have 0 times that 45 meters per second times 0.1 kilograms, and then you would still have 0. All right, hell yeah. So that was a good introduction, but now we're going to get a little bit tricky. So we're going to have a catcher right here, and we're going to have someone throwing a ball from right here. So this ball is going to be thrown that direction. And then guess what? Another person's going to throw a ball this direction. That's why I kind of made this scenario. And then so this catcher is that origin. And now we're going to assess what's the angular momentum of this. And, oh man, I'm going to go upstairs because if we're starting to put numbers on these, which is a good thing, I definitely want to know how many meters this is away. And we'll try to get an average speed for someone throwing, from like third to first. All right, catch on the flip side. All right, hell yeah. So we're back. And, yeah, so it's 90 feet and 27.5 meters, 27.4. But we'll just say... We're just going to say 30 meters. Now, 45 meters per second is pretty fast. It's closer to 100 miles an hour, right? So we're just going to go 40 meters per second. And so this is going to go to 4.0. You know what I mean? So that was the number on that. So we're going to be throwing at 40 meters per second. Our baseball is still 0.1 kilograms. And I think that's right. I think a baseball is 100 grams. It's probably not, though. It's probably 200 grams. Let me look that up. All right, hell yeah. So a baseball is like 145 grams, but forget that. We're just going to say it's 100 grams, so 0.1 kilograms. Okay, so sweet. We're good there. And now we can assess this situation. So, and the cool thing is these baseballs don't need to be attached to anything. You know what I mean? We have this point O right here, center of mass of this catcher, just facing this way, and we have a system. And now this system has linear momentum, and this system also has angular momentum. So right now, we're going to figure out the linear momentum. Linear momentum says, hey, this is a mass and it's got a velocity. So that's going to be 0.1 is the mass, 40 is the velocity. Over here, 0.1 and 40. So we have angular momentum of 4 and 4. So our total angular momentum, I'm using our linear momentum. That's what we're solving for first. The initial linear momentum is 4 plus 4 is 8. Sweet. So now what's the angular momentum? So if we go back to what causes angular momentum, you know what I mean? So it would be like, this scenario is like, hey, I've got two forces. I've got two people are going to open this door. We're going to put a force this direction on the doorknob, and then this person's going to come in and put a force this direction on the doorknob. Okay, sweet. So the doorknob sees a total force, maybe like, you know what I mean, of both of those. Even though there's it's not super similar to linear momentum, but anyway, let's just go with it. So but only one of these forces is causing a moment. The same thing with angular momentum is that both of these have a mass and velocity. But look at this. This one's in line with the center of mass of the catcher. So there is no distance this way or that way. So the distance to this one, and, well, sure, you could say, well, isn't this the distance to that? So let's do it. Let's say this is R. Well, yeah, this is the distance to this baseball. But guess what? The velocity is in this direction. So if we did the right-hand rule, we would be putting our hands in the direction of this baseball, but then let's say you're throwing the baseball the other direction. You know, we put our hands in the direction, but then usually you have to curl your fingers like this way, that way, you know, any direction. You know what I mean? Basically, your thumb has to be in some sort of direction. You can't put your fingers in the direction of this distance and then just jab them forward or like pull them back, which is where this direction of this velocity is. And it's because it's a cross product. So if you learned anything today about what a cross product is, you just think 90-degree angle. You have this and this has to be at 90. If they are at 90, just multiply the numbers together. If it's at 180, then it's 0. And then if it's anything in between, well, it's going to be in between multiplying them together and 0. You know what I mean? And then so you can just use your guessing skills or just use, you know what I mean, trigonometry. All right, hell yeah. But this case, this is 180 degrees. You know what I mean? It's either 0 or 180, depending on how you look at it maybe. And so there is no angular momentum. So we did this distance crossed with, yeah, we did have a number for this distance. We do have a number for the velocity. But because, and let's, I guess, slow it down. If we do have, like the doorknob scenario, we're going to have, the moment is going to be R cross F, and the scalar component, which you would say like, hey, what's the magnitude of the moment? Just kind of the number I'm interested in. That's going to be, hey, just this distance times the force, you know, cool, the number on the distance, the number on the force, but then sine of the angle between so here on the door, if this is the force, this is the distance, we have 90 degrees. Sine of 90 is 1, and so you're just going to have, you know, it's just going to be 100% of R times F. That's going to be the number that you're going to get. Now, if in this case, this distance was this way, this force was this way, your angle is either 0 or 180. Sine of 0 or 180 is 0, and then so you have, you know, 0%. Now, if, you know what I mean? And then so any angle in between will give you some sort of ratio of what you'll be using. You know, 0 to 1. All right, hell yeah. So I don't think we have to beat that one to death, but so sweet. So we have angular momentum. This one, because the distance, it's you do have a distance, but it's because the angle between them is 0 or 180, and that's the reason this cross product generates you know, a 0. So this baseball generates 0 angular momentum. Now this baseball over here, I mean, you could say, hey, look at this. This is the distance also. You could say this is the distance, but it's a vector, and it has two different components. You have a component, let's say Rx, you know, in that direction, and then you have Ry. Well, you can see that this component is in line with it, and again, it's going to be the same thing that we did here. If you go from here to there, and then this velocity is in that direction, you either have a 0 or 180 degrees between this distance and this velocity. And then so this component's going to generate no angular momentum. It's only this component. So if you can see that right off the bat, I mean, you know, if I'm going to... Alright, so here's the analogy here. If I'm going to go open this door, I'm not going to stand like 10 feet out here and then be like, okay, I'm ready to go. I got a force, you know, I'm going to apply a force with my hand, and it's going to be along this path, and then let's analyze it from the hinge, and then like, hey, I'm this far away, you know what I mean? But I have two components. I have one component that's just in line with this, that has absolutely, yeah, so this component is that distance. We're just going to call it Ry, and this is going to be Rx. So this distance is in the same direction as the force that we're applying. So that's going to be analogous to like, oh, because a lot of the higher up videos will be like, well, let's not assume anything. We're just going to, hey, take the moments from this point, and we're going to identify a force like starting from this point is going to be along that axis. And then so heck yeah, here is going to be your distance, and it's going to have two components, one this direction, one this direction. This direction, and that's why is irrelevant, because it's in the same direction as the force that we're applying. 0 or 180 means that sign is sine of 0 or 180 gives you a 0, and then so multiplying this distance times this force, you know what I mean, gives you 0 for the for just kind of what's opening the door. That doesn't help you open the door. It's only this perpendicular distance away from the hinge and where you're applying that force once you actually do hit the door that's useful. And this analogy can be a lot better because, hey, let's say this is just a really long door and you open the door all the way up to here, you know what I mean? So now that the door is fully open, but then you go and push along this path, you know what I mean? It's a horrible path. If the door's already open, you would want to push from this direction, but now visually, you know what I mean, now you're pushing in this direction. And so, you know, if you were pushing in this direction, you would get all of this width of the door helping, you know, and obviously we just made our door really long, like a barn door. But if you push with this angle, now it's like you're trying to close a barn door with the same leverage, distance, and force and distance of just a normal door, you know, with a normal doorknob. So that's kind of the analogy there. Alright, hell yeah, I should say analogous. It's not an analogy. Okay, so hell yeah, so booyah. So you have these two baseballs. This doesn't generate any angular momentum. The angular momentum, we're just going to say L1 of that baseball and L2. Well, hell yeah, this does generate momentum. And so what do we multiply? This distance 30, the mass of 0.1, and the velocity of 40. So we're going to have 30 times 40, I think that's going to be 1,200, and then times 0.1. So we're going to have 120 as our number for the angular momentum. So booyah, throw two baseballs, one hits this catcher, the other just goes by the catcher. But the whole system has an angular momentum of 120. Now, I think it is bizarre that you're just like, well, I have no effect on this baseball. This catcher can't catch this baseball. It doesn't have like a like a, you know, whatever that Stretch Armstrong guy arm is, you know what I mean? And you can't do anything with that baseball. But still, the system has an angular momentum. If the catcher did have to reach out a Stretch Armstrong arm, it would have to apply a force out here a distance away, and so to slow this down. And if it changed the velocity, if you did change the velocity of that ball, then you would effectively change the angular momentum of the system. So, and I kind of want to take this analogy back to this as much as possible. So, when this brick, this square starts coming in, it has linear momentum, like a lot of it, you know what I mean? But even when this brick is over here, it still has, like, the mass molecules along this plane are not contributing any angular momentum. It's only the mass like these mass particles and their initial velocity are contributing hella because this distance s is at the greatest. Now, these molecules right here, you know what I mean, of mass, still have that incoming velocity, but their distance is much less, you know what I mean? So they do contribute a little bit to the angular momentum, but what I'm getting at is the angular momentum coming in was already a number. Now, this is where you can't compare apples and oranges. You can't say, okay, you have linear momentum coming in, and then you can't compare that to the angular momentum. Angular momentum, I guess you have to take from a point, but I guess what I'm getting at is the angular momentum of the system coming in was the same as when it hit. There was no change in angular momentum at all. And even when it hits, you have a conservation of angular momentum, and that's going to be the next thing that we kind of look at in more detail. And I have another one of these sheets of paper, we'll clean it up. But we're already alluding to it. You know what I mean? The catcher can catch this baseball because this baseball had no effect. It had no, it did not increase the angular momentum. You know, because this baseball has mass and velocity coming in, there was no angular momentum of the system of this baseball. So you can catch it. You can have an inelastic collision. It doesn't have to bounce back, or you know, you can just catch it. So you once this baseball gets caught, you have an elastic collision. That mass totally stops. So that is analogous to this mass right here, completely coming to a stop. Cool. And now this baseball just keeps going, but it still has the same angular momentum. Even when this baseball gets to hella over here, you know what I mean? Hey, didn't the distance change? Well, yeah. And then here is the velocity. And then look at this. Here's the components. You have one component of the distance going this way, and that's going to be the perpendicular to this velocity. This distance is the only one that's going to be a driving force of the number for this angular momentum. This distance can get hella, you know what I mean? This distance, we're just going to say in the y direction, kind of that ry. It doesn't really matter. Your angular momentum isn't changing. And this, so now, because this is where it's just like, well, how do you explain this? I think this is how I visualize it in my head. Let's say I could instantly construct a massless, rigid rod. You know what I mean? So cool. I think we got it. So you instantly construct a massless rod. This is the only mass on the system. It has velocity. And on this end of the rod, I have to generate a torque. I either have like a little wheel, or like I have a dowel that sticks up and I have to squeeze that dowel. I basically have to apply a torque, you know what I mean? Whether it's a dowel that sticks up and I put pressure from fingers on this side and fingers on that side, that's generating a couple, you know what I mean? So you have a couple that gets generated with a force, and then the distance, the diameter between that dowel, you know what I mean? Or just, you know, a torque in general is just, you know, you could just have one lever arm sticking out and then you just have a force on that. But what I'm getting at is you need to generate a torque from, not necessarily this position, but, well, from this position for sure. And when you do that, let's say we want this baseball to come to a stop right there. So in the next 1 second, this baseball is going to come to a stop. We have to apply a torque on our massless rod. So I guess what I'm getting at is it doesn't matter whether this massless rod is hella out here or just like, you know, sky's the limit over here. Is the only thing that makes this baseball hard to bring to a stop is this distance right there. It's this R cross momentum. So this perpendicular distance is the only thing. So when the baseball passes this line and we put that massless rod on it with a dowel and we squeeze that dowel and we have that baseball come to a stop in a second, it took an amount of torque to do that. That's going to be the same torque that's need to be applied if you let the baseball get the hell over here, put a massless rod on it, and have it come to a stop in a second. So that was probably the most brilliant, you know, thing that I came up. Well, I mean, just part of this video is just like, thank goodness you actually told us something useful, and that was a very useful visual representation of what's going on with angular momentum and how, you know what I mean, this can get way out here but still has the same value for angular momentum. We do an absolute value sign just to be like, hey, just what's the number on it? And it does have direction. And the direction is because let's say you do a massless rod out to here and then you stick a dowel perpendicular to that. Well, that's the you know what I mean? So it's your distance. And then, so right hand rule, here's my distance, here's the velocity. So here is the direction of, so down at a perpendicular to that and that. That is going to be the vector of angular momentum. And I think I'd do a double arrow. I don't even know if that's probably not even commonplace. But I do it on that because you're just like, because it's very similar to, I do double arrows on moments, especially if they're going through hinges. I'll have to see if that is a common thing or when double arrows actually gets used. Because you have because what you wouldn't want to do with this moment going through hinges is you wouldn't want to assume this is useless. Because if you have a force that's like pushing on the hinges, well, you ain't opening that door. But if you have a force out of a distance, perpendicular, you have that R cross F, hell yeah, you get a number and a vector for this moment, and it's in the axis of those hinges. So the same thing with angular momentum. This is the axis down, and it has a number. And if you want to apply a torque, well, hell yeah, you're going to have to apply a torque in the same, well, probably opposing. You're going to have to apply you're going to have to apply an R cross F. So you're going to have, so I just gained some valuable information. So if my linear, what is this called? Angular momentum. If my angular momentum, after we do the R cross F, R cross the velocity of, it's the linear momentum, that's going to be down. If I want to change that, if I want to increase it, hell yeah, just keep it going, you know what I mean? But if I want to reduce the angular momentum, I need to apply a moment, you know what I mean, along that same point, in the opposite direction, but in the same axis as that angular momentum, and it's going to be an R cross F. So R cross, and then we're going to apply a force over here, whether you're a Stretch Armstrong or you have a massless rod connected to that baseball. Alright, hell yeah. So now we're actually going to do kind of the actual problem here. We're going to have 3 baseballs. So we're going to have a baseball being thrown that way. One from maybe the shortstop. I don't know. He's just throwing it that way. And then from second base to first base. So here's going to be our velocities. And we got 3 baseballs. Maybe 1, 2, 3. We do have that one catcher. And here's our origin. So there's our origin. This mass of this baseball. We have linear momentum. We have M1, V1. We have M2, V2. We have M3, V3. So our initial linear momentum is adding those 3 up. Okay, what's our initial angular momentum? This provides 0. This is going to be half of 30. So this was going to be 30 meters, the total distance. We have a speed of velocity is 40 meters per second. Mass of a baseball is 0.1 kilograms. Okay, so we're going to have, I'm just going to use my calculator. So this one is going to be 30 times 40 times 0.1, and we get angular momentum of 120. This one's going to be 0. Angular momentum of this is going to be 15. It's just going to be half that, so it's going to be 60. All right, hell yeah. But sometimes I just don't want to make little errors, so I'll use my calculator. All right, so, and what's going to happen is this baseball is going to get caught right there, and then these are just going to keep moving. And I swear we're going somewhere with this, because now from this point, these both have the same velocity. You know what I mean? The velocity of this one is still, V2, V3, and V1 is equal to V2 is equal to V3. We're just going to say is equal to V initial. You know what I mean? And we're going to say that's going to be, and then this is going to be equal to V final. Okay, but that is not what we have with a rigid body. A rigid body, if what happens with this is that, hey, this one stops, this point right here, and then this halfway point right here, these hella do not have the same velocity. This point right here has half of the velocity. So if we say V2 final is V3 is just 1/2 of V3. And then V3 final is what it is. So there you go. So due to continuity, that's what happens. All right, damn it. You know what I mean? I think I created my first problem, and I think we can end on this problem because it's gonna. You can probably do it faster than I can do it. But we just said that the angular momentum initial is going to be 120 plus 60 plus 0. Looks like it's 180. And because angular momentum is conserved, our angular momentum final is also 180. But the only constraints is that V2 and V3 have to be equal to each other. So V2 final has to be equal to V3 final. Okay. But we still have these equations that say angular momentum is the distance times mass and then velocity. So what's the distance to this one? It's 15. The distance to this one is 30. Okay, so, but the cool thing is all these are perpendicular. You know what I mean? If this is our distance to this one, that's our distance vector. Here's our velocity. That's a 90-degree angle, so we don't have to use any sine of any angles. You know what I mean? That's all going to be one sine. They're all going to be sine of 90. So when we multiply, so I've not done this one, but it should be fairly intuitive. But that's where I get tripped up doing harder problems, because when I came across this one, I didn't even understand why angular momentum was conserved, and it took me a few months to even kind of figure out what the hell was going on, and then start to figure out ways that I would like to teach it, and why wasn't it taught that way to me. And so that's kind of my style. Even though we're pretty unpolished, we just kind of go for it. So still, thanks for joining me. I really appreciate that. All right, hell yeah. And then it's on, because we have to kind of figure out this problem. It shouldn't be too hard. Okay, so let's do it. So the angular momentum final is going to be it was distance. So we got 15 times the mass. That's going to be 0.1 times the velocity. And what we could say to compare it to this, because what happens to this one is you do get an omega. So let's introduce that concept. That, hey, let's say both these baseballs have to travel with some sort of omega around this axis point. And then, so what does that mean? That means that we're going to have, I gotta pause the video. Well, I only paused the video for a couple seconds because we really have to go over the basics, because I've glossed over what omega is. Omega is angular speed in radians per second. And so let's do a circle. And let's say we're going 90 degrees a second. Like we're going 1, 2, 3, 4. So it takes 4 seconds to go around a circle. Now we need to figure out how many radians are in a circle and what the hell is a radian. So this is the radius. If we cut a string and draped it around the circle, we'd probably get to about there. So this linear distance is the same thing as the radius, and that is all a radian is. And you can get about, there's about 6 of these strings going all the way around, but there's a little bit more. There's 6.28 strings, and this number is 2 pi. So sweet. Hell yeah. Now, here's my other trick with radians. Like radians, like no one knows what the hell they are. So I always say like radians times radius is something normal. And in this case, it's this length. This is arc length, S. With angular speed, radians per second, or radians times radius is something normal. That's tangential velocity. Angular is just radians per second squared. This is angular acceleration. Same thing. Radians times radius is something normal. That's just tangential acceleration. All right, so that's the only way I can keep, that straight. And so if we wanted to find the tangential velocity here, I just go back to this, and okay, so that's going to be omega r. Okay, hell yeah. And then, and I'm glad I did this, because angular momentum, yeah, this is the only place I have it kind of written. Angular momentum is this distance crossed with the mass crossed with the tangential velocity. Tangential velocity is the distance and then omega. So this distance comes up twice. So let's do this. So now we're going to say, what's the angular momentum about point O? Is, and this is going to be final, is going to be this distance r. So we got 15, and we're just going to do r right there. Crossed with the mass, so that's going to be 0.1. Crossed with the tangential velocity, so let's write this again. Angular momentum is r cross m omega r. So there you go. So, and I don't know if what you would, we've already, let's turn this into a scalar. So we have angular momentum, and you can do this. Absolute value of it is just r m omega r. And I would leave it like this, actually. I think it's crazy to just do like I don't know how they clean it up. Do they do mr squared omega? Is that how they clean it up? Why rearrange all the letters where you don't know exactly where it came from? So we're going to stick to this, and I think that's a really good way to do it your first go-arounds. Because now you can see that we don't know what omega is. That's what we're trying to find out, and we have this 15 again. Cool. So that's going to be the angular momentum of that. We're going to add it to this one. We have r. It's going to be 30. Baseball's 0.1. So we have rm. We don't know what the omega is. Put just a little question mark. And then we have that r again, 30. Okay, hell yeah. And we know that the angular momentum final is angular momentum initial. And I'm just going to throw in a huge, this, all I've done is used, literally this equation, and then under an understanding of what's going on with angular momentum. At no point, I swear, some of the equations they use in the letters of H, and I have no idea what's going on. I don't want to use any of that. I want an intuitive approach to learning angular momentum. So that's kind of what I'm giving you, and giving myself as well. Because, I swear, anytime textbooks get crazy, it's just no way. You know what I mean? I'm going to find a way to teach myself, and hopefully you, just a better approach. All right, hell yeah. Alright, I got excited there. So yeah, angular momentum initial is same as final, and initially it was 180. So hell yeah. So now we just have a very basic, Yeah, this should be pretty easy to solve. And, yeah. Should we solve it in a tricky way? I don't even know. Damn it. Oh yeah, 15 times, let's use our tricks. 15 times 15, that's 10 times 10 is 100. 5 times 10 twice, that's 100. 5 times 5 is 25, that's 225. And then we're going to have 0.1. So we got 220, so we got that plus, and then this is going to be 30 times 30. That's going to be 9 with 2 zeros. Hell yeah. But it's going to be 90 omega. Yeah, I feel like I already messed it up, but no, because 30 times 30. Oh, this is bizarre. This messes with my brain. It seems like 30 times 30 should be just be 4 times 15 times 15. And that's exactly what it is. Okay, because double this is 45. Yeah, perfect. So we got to check on reality there. I don't know what 90 plus 22.5 is, but I do know what 90 plus 20 is. That's 110. So we have 100, and so we have 112.5 omega, 180. So sweet, omega is 180 divided by 112.5. 180 divided by 112.5, and we have omega is 1 radian per second. And is that right? You know what I mean? I have no idea. But we can go back and figure out what the velocities were, because we know. What's the tangential velocity? What was the equation for that? Something normal is omega times radius. So we're going to have 1.6 times 15. 1.6 times 15, so this is 24. So we got 24 meters per second. And then we're going to have 1.6 times 30. This one's going to be 48 meters per second. So there you go. We had initial velocities of 40 meters per second on all three of these. This one sped up. I think that's way cool. And this one hella slowed down. All right. Booyah. So now that we know the velocities, now let's just recheck using this equation. So we're going to have, and just our calculator, we're going to, for this one, we're going to have 15 times 0.1, the mass, times 24, plus this one, we're going to have a distance of 30 times the mass, 0.1, times 48. And booyah, it should equal 180. Hopefully I did something wrong and we find some errors. But hell no. You know, we did it right. We even figured out what the radians per second was. No one knows what radians per second is, but if we go back, and what's 1.6? So if this is 1 radian, and this is 6 radians, so 6 radians per second is this, like 0, 1, 0, 1. 1 radian per second is this, 1, 2, 3, 4, 5, 6. So 1.6 radians is almost like 90, so it's like 0, 1. So cool. So let's go from here and then do a 90. And so basically this ball, if it was traveling, no, I don't know what. Oh no. Yeah, this is 100% right. If this ball is going to travel 90 in 1 second, so there you go. It's going to go 0, 1. Because that's 1.6 radians per second. 1.6 times 4, yeah, is about 6. You know, is a full circle. Yeah, that's interesting. Yep. And so that must mean, yeah, obviously, if this is 30 meters and the speed is 40 meters a second, it's going to take hella less than 1 second to do this, and this is going to take 1 second to do that. So we're going to come in with 40, and then it's going to speed up. You know what I mean? So that's, and I think that's also a good trick to do. Like, hey, can you actually do a diagram? And if it's in seconds, that actually makes sense. Can you actually just kind of repeat, you know, visually what's happening? Because this ball is coming in at 40, and then it speeds up instantly if it's a rigid body. So how did we go from 3 baseballs independent to this? And I totally forgot to do that. So let's all right, hell yeah. So this is what you would do to this problem. You would do a massless rod. You would connect all 3 baseballs with a massless rod, and now you have a rigid body of 3 point particles. You have 3 baseballs being thrown at the same time, connected with you know, a massless rock. I mean, just think very light wood, but then it's so light it doesn't exist, but it makes them rigid. And then so when this catcher catches that first ball, that's all this catcher can do. You know what I mean? The catcher can just absorb the impact just like this. Catcher's not doing any sort of torque on the system. And then so these continue with their same angular momentum. Yep. And oh, and the other aspect of this problem is I wanted to see, because I think that these, I'm just going to throw this out there. I think these two, if you added the linear momentum of those two baseballs, I think the linear momentum of these two baseballs equal the linear momentum of those. What you've only done is you just take, the only thing that you've done is taken out the linear momentum of this. But I definitely want to show that the linear momentum, so let's do that. Yeah, we need to figure out what the linear momentum of the final system is. This baseball has a mass, but it has no velocity. So linear momentum, again, is just mass times velocity. It is it a scalar? Yeah, I think linear momentum is just a scalar, because yeah, you're just identifying masses, and the velocity is just in any direction it's going, like that. Whatever direction that velocity is going at that point, that's going to be its linear momentum. All right, so we got 24. So right here, so we have 24 times 0.1, and then here we got 48 times 0.1. So we have that plus 2.4. So we have a total linear momentum of 7.2. Initially, this one had a linear momentum of 4, and this one had a linear momentum of 4. 40 times 0.1. So, oh, so this was interesting. You know what I mean? So, I do not know how to explain why the linear momentum of the system. It's because the angular momentum is conserved. You know what I mean? That's the only thing that's conserved is angular momentum. And I'll have to go back to the drawing board of like what is angular momentum? That's fascinating. Alright, so hopefully I made a mistake, or I don't know, this is tripping me out, because so this had a linear momentum of 4. So we have 3 baseballs, each have a linear momentum of 4, so that's going to be a total. So the linear momentum initial is 12, the linear momentum final is 7.2. So we got, you know, here's the velocity times 0.1 mass, so we got 4.8 plus 2.4. And so that's going to be 4 plus 2 is 6. 8 plus 2 is another 1. That's 7 plus the extra 2. So 7.2. And it's just it's fascinating to me that these two baseballs have a linear momentum of 8, and but the linear momentum of the whole system is reduced. But yeah. So I'm going to be pondering that one. Because I just figured the linear momentum of the system is reduced because we stopped this baseball. You know what I mean? That was the only thing contributing to the change in linear momentum from initial to final, but that must not be the case. Alright, hell yeah, but that's it. I did what I wanted to do, you know what I mean? You know, we show why angular momentum is conserved at this point by representing a catcher's mitt. At that, it can catch all the linear mass and velocity molecules that come in that are on that line, you know what I mean? So like all of these are for sure, you know what I mean, no longer in the kinetic. Like if this thing has kinetic energy, every chunk of mass has a velocity. You can calculate its kinetic energy. All of, well, only this molecule dead stops, and then all the others start to rotate. But because you have some molecules that come to like a dead stop, then your kinetic energy final is less than your kinetic energy initial. Alright, so I guess before we go, the other thing with the scalar component of this, it's r, m, omega, r. And then so I totally now recall. So you do mr squared omega, and then this term is your mass, second moment of mass. See how you have mass and then your distance squared? And so it's a scalar component, but it's mass moment of inertia, it's moment of inertia, it's second moment of mass, just like you would have a door with a distance out to the hinge and a force. This is going to be your first moment of force. You know what I mean? So we say what's moment is going to be R cross F. It's your first moment of force. The first means that you're only taking the distance one time. So you have a first moment of force. With mass, let's say you have an I-beam, and here's your kind of center point. Let's say this is your hinge, and then we're going to go out from the center to a chunk of mass up here, and then so this mass, here's your distance, but we're gonna do this distance twice. So we have the second. So moment of inertia, or second moment of mass, is that distance twice times the mass, the portion of mass that's out there. So we have the second moment of mass. Distance twice, that mass, and then multiplied by that mass. So that's where this is called the second moment of mass. It's not just second because it comes in order of other, but yeah, it's that's where we would get that term second moment. All right, and so second moment of mass is going to be, how did we say it? mr squared. Yeah, so even that, you know what I mean? I would rather have it written r squared m. But anyway, and I like how doing the scalar. I always do this because this totally spells it out. You had your r cross mv, and there you go, r cross mv. You know what I mean? And then v tangential was the angular speed times the radius. Radians times radius is something normal. That's tangential velocity. Okay, hell yeah. So, you know, you still have no skills to actually solve this problem and figure out the omega once you know the mass of this square. You know what I mean? Like, literally, I don't know how to solve this problem from an intuitive perspective. I do know how to, like, hey, let's just turn this problem into, you know, masses at the corner. You know what I mean? And then maybe a mass in the middle that's maybe 4 times. You know, doing this and then just turn it into 8 different little masses. Yeah, we could totally turn it into this baseball problem and get a representative. But it's not going to be, it might not even be very accurate to do that. But it's a step in the right direction. You know what I mean? Like maybe you're not going to be an order of magnitude of 10 off, but you might not even be you might be you know, 200% off for sure by doing that. But maybe I'll do that, you know, maybe for the next problem, and just guess. You know, if we put all the masses, like the original problem says this has a mass of 9 kilograms. Well, if we put the masses in the 4 corners, is that representative? And it's like, no, because there's a lot of mass in the center of this thing. You know what I mean? If this square was actually, you know, like a piece of steel, a hollow tube, well, sure, then you could put the masses at the corner and then maybe put a couple here. But because you have so much mass in the middle, I don't know. I would put masses at the 4 corners and then 4. I would divvy it up into 8. You know what I mean? 1, 2, 3, 4, 5, 6, 7, 8. These 4 being right in the center. And then maybe even 5 or 6 in the center. I don't know. You know what I mean? So what would be, like, what would represent a square moving if you did that, if you simplified it in that way? That would be a fascinating one. But for another day, thanks for joining me on this one, and hell yeah.